And I like to talk about the intuition behind how things work before we talk about the math. There's different types of signals. You can have a low frequency discrete time signal, and you can have a high frequency discrete time signal. A low frequency discrete time signal that's finite length might look something like this. So it's definitely finite length. It's a low frequency signal of n equals 5. And it's low frequency because intuitively, if you look at it just over the range, where we're going to say it's non-zero, just over its defined range, this, if you were to link those things, it certainly changes a little bit, but it doesn't change a lot. It's mostly static. And compare that with a high frequency discrete time signal like this. This is in fact close. So here's another 5-length discrete time, finite length signal. But you can see that in terms of discrete time, at least, this is about the fastest frequency you can get. You can't get much faster than it alternating. Now, again, it's not a perfect high frequency signal. There's clearly some other components in here because it doesn't look like a perfect sine wave. These top things aren't all the same length. These bottom things are, well, they're pretty close, but it's not perfect. The way that you would see this in the DTFT is like this. So firstly, this discrete time DTFT, from our definition over here, you can see it's got this e to the minus j omega n. So that means that this is going to be a complex number. It takes one real valued input, omega, which is always real valued, uniquely between 0 and pi, and it outputs some complex number that has a magnitude and a phase. You could think of it as having a real part and as an imaginary part, but we know that for complex numbers, it gives us the most intuition by not writing them as a real part plus imaginary part, but rather as a magnitude and an angle. So I can't draw both a magnitude and an angle versus omega on a flat screen. I have to choose one of those things. And intuitively, the most important part is to draw the magnitude, because we want to see this for this discrete frequency, for instance, if it passes a high voice or if it stops the high voice. You could create a discrete time filter that is tuned to remove a guitar or a vocal, say, from a music performance. And for that, we'd want to look at its magnitude. In fact, usually we want to look at its magnitude. Now we're going to look at a signal. How much high frequency does this have? It has a lot of low frequency, but it doesn't have a lot of high frequency. It has some. It's not all low. It has some, but not much. Of course, it's a magnitude, so it can never dip below 0. And compare that with our DTFT of our high frequency signal. So now the x-axis is omega, its frequency. And now it might look something like this. It has, if you took the average, it might be not quite 0. So it might have a little bit of low frequency energy. But now most of this frequency energy is going to be concentrated in high ranges. So that's pretty much it for the intuition about what a DTFT is. You can almost see it. Big intuition problems I see often students have is that they can't switch the fact that this is omega. They think that this is somehow still n, and if it's going up and down here, it should go up and down here. They don't realize that they're trying to match this with the frequency of a cosine wave. And of course, here the frequency of the cosine wave would be low. So it's got a lot of low frequency. Here it's high, so it's got a lot of high frequency. Now this is, even though it's discrete in n in time, the DTFT is continuous in omega. The way that it works is we say that the frequencies are unique between 0 and pi. So for greater than pi, it looks like a mirror image. Let me try that again. Looks like a mirror image around pi. And then if we continued it on, it would repeat again. Similarly, between 0 and minus pi, it's a mirror image in reverse. So what does the y-axis represent in the DTFT? It represents the magnitude of the DTFT. What we're graphing is the results. If we put this signal up here, this sequence, which is, say, 1, minus 1, plus 3/4, minus 1, plus 1 1/4, if we put that into this summation sign and sum that versus this complex number, we get a complex function out of omega. It's of omega because we've got this omega up here. And so then once we sum it, we remove the n and we're left with just an omega. Now we want to plot that x of omega, that DTFT versus omega. And so this is the vertical axis is what this number converts to. as a magnitude. All right, same thing we can do in reverse. We usually only plot it between 0 and pi, but if we wanted to plot it over an extended range, we could, and it would look like just the mirror image going through here. Same thing here. For negative pi, we'd have a mirror image around the vertical axis. All right, so that's it for the DTFT. If you see a signal in the DTFT that has a lot of stuff around that's high, whose magnitude is high around pi and low around 0, then it's going to be a high frequency signal, and it's going to look like this. If you see something, a magnitude of a DTFT that has a lot of power for small values of omega and very little at high values of omega, high meaning around pi, that means it's going to be a relatively unchanging signal.